Hey everyone, and welcome. So today we are diving deep into one of the most exciting and frankly most misunderstood topics in all of science, quantum computing. And I want you to just for a moment forget everything you think you know because we're about to uncover the real story behind these incredible machines.
All right, so let's just kick things off with the number one popular idea you hear about quantum computing. This idea that they get their power by trying every single possible solution to a problem, all at the exact same time. I mean, it sounds incredible, right? But is that actually what's happening?
Yeah, in a word, nope. As quantum computing expert Scott Aronson puts it, that's just not what they do. If you just measured a superposition of all the possible answers, you just get one back at random. It's kind of like shaking a box of lottery balls and just grabbing one. Not exactly a genius way to solve a problem, right? The real story, it's so much cooler.
So let's really tear apart this whole quantum parallelism myth and find out where the true power of a quantum computer actually comes from.
And that, of course, brings up the big question. If it's not some brute force supercalculator, then what on earth is it? The answer isn't about raw power. It's about elegance, something much, much more subtle.
And here it is. The secret is structure. See, quantum computers are specialists. They're not your jack-of-all-trades computer. They are built for one thing, really, finding hidden patterns and rhythms in data. Think of it like a hidden mathematical beat that classical computers just can't hear. Okay, think about it like this. Imagine two different problems. The first is finding a needle in a haystack. The second is finding a repeating pattern in a super long sequence of numbers. The needle in a haystack, that's just brute force. You have to check every single piece of hay. But finding a pattern? That problem has a hidden structure, a kind of beat. And that is what quantum computers are designed to hear. Let's make this real with an example from a super famous quantum algorithm, Shor's algorithm. This is the one that really freaks out security experts. By finding the repeating pattern, or the period in a sequence, just like this one, a quantum computer can figure out the prime factors of a massive number, a task that would take a regular computer, like the one you're using now, literally billions of years. Yeah, that's the power of finding the beat. Okay, so how? How does a computer actually find these hidden patterns? Well, it all comes down to a brand new kind of building block, a new kind of information bit, the qubit. A classical bit, the thing that powers all our current tech, is like a coin that's already landed. It's either heads, a zero, or tails, a one. That's it. It's definite. But a qubit is like that coin while it's still spinning in the air. It's a mix of both heads and tails at the same time, a shimmering cloud of probability. And that spinning coin state, that has a name. It's called superposition. It allows your qubit to live in this strange world of probabilities, holding onto the potential of being both 0 and 1. And this is the absolute key. It's what allows a quantum computer to check all those different possibilities, all those clocks we're about to talk about, all at the same time. But it gets even weirder. When you link these qubits together through something called entanglement, their fates become intertwined. What happens to one instantly affects the other, no matter how far apart they are. And this is where the power just explodes exponentially. Two of these entangled qubits can process 4 bits of classical information. 3 can process 8. 4 can process 16. You see where this is going? This is what gives quantum computers their mind-boggling horsepower. All right, quick recap. We have our problem, finding that hidden pattern, and we have our tool, the amazing qubit. So now it's time for the main event. How do we actually put these two things together to find the hidden beat? Right? This is the million-dollar question, isn't it? So how do we get from this weird spinning coin idea to a real answer? Well, believe it or not, the best way to understand it is with a really cool analogy involving a wall of clocks. So I want you to imagine you're in a room, and on one wall, there are just hundreds of analog clocks. But these are weird clocks. One of them ticks around once every 24 hours. The one next to it, maybe 25 hours. Another one, 26.3 hours. Just imagine a clock for every single possible period you can think of. Okay, you with me? Now remember that sequence from before, the 2, 4, 8, 1 pattern? You take that sequence, and for each number, you walk up to every single clock on that wall, and you move a little thumbtack 1 inch in whatever direction that clock's hand is pointing. You do this over and over for every number in your sequence.
Now let's think about what happens. For most of these clocks, the ones that are out of sync with your pattern's real period, like that 25-hour clock, the direction is going to be random, right? The thumbtack moves an inch up, then maybe an inch down left, then an inch right. It's all over the place. Those movements basically cancel each other out. And at the end, the thumbtack hasn't really gone anywhere. This is what we call destructive interference.
But here's the magic. For that one special clock, the one whose period perfectly matches your sequence, in our case, the 4-hour clock, something incredible happens. Every single time you go to move the thumbtack, its hand is pointing in the exact same direction. So the thumbtack moves an inch, then another inch in that same direction, and another. It just keeps going, traveling farther and farther away from the center. And that is constructive interference.
And that's it. That is the core trick of a quantum algorithm. Superposition is what lets you set up all those clocks and check them all at once. Then, the quantum computation uses this beautiful dance of interference to make the wrong answers literally cancel each other out, while the right answer gets amplified, louder and louder. So when you finally measure the qubits, all you have to do is look for the thumbtack that traveled the farthest. And boom, there's your hidden pattern.
So, okay, that's the theory. Super cool, right? But what does this actually mean for you and me, for the real world? Because this isn't just some wacky physics experiment. We're standing right on the edge of a new quantum frontier, and the implications, they are massive.
And I am not kidding when I say massive. Check this out. Projections from McKinsey are saying that quantum computing could create up to 1.3 times trillion dollars in value by 2035. That's trillion with the T. This is a technology that's getting ready to completely reshape entire industries. So where does all that value come from? From absolute game changers. Remember finding those hidden periods? That's the heart of prime factorization. And that's the key to breaking almost all of the encryption that protects our data today. Then you have quantum simulation for designing new drugs and materials, optimization to completely revolutionize logistics and finance, and even quantum AI to supercharge machine learning.
Okay, but let's take a breath. We are not there yet, not even close. The road ahead is packed with enormous challenges. These qubits, they're ridiculously fragile. The slightest vibration can mess them up. We need to scale from a few hundred qubits today to literally millions. And trying to correct all their errors at that scale, it's an unbelievably hard engineering problem. Oh, and on top of all that, there's a huge talent gap. We just don't have enough people who know how to build and program these things. So, here's the takeaway. Quantum computing isn't some kind of magic that tries everything at once. It's a whole new way of computing that leverages the weird rules of quantum mechanics to see the hidden patterns in the universe. The race to build a machine that can truly unlock this power is absolutely on. And it leaves us with one big question. Are we ready for what comes next?